Hello and welcome back to Math Class in Session. Today, inverse functions. Suppose that an equation for determining the cost of a taxi ride is a linear function cost for n. C of n equals 0.75n plus 2.50, and that would be the cost in dollars for n, the number of kilometers traveled. The inverse function tells us how far we can go for a given budget. If I have a certain amount of money, how far can I go for this amount of money? That's what the inverse function would help us with. So we have the original function, the cost for a given number of kilometers. Using our machine analogy, we would input n, because the input always goes into these brackets, into this part of the equation. Something would happen to it, and the output would be the cost for that n, or C of n. In this case, what happens to it is it gets multiplied by 0.75, and then $2.50 is added to it, and for the output cost. The inverse function, we want to input a cost. So we simply feed the machine from this end, and the inverse happens to it. Inverse meaning the exact opposite. So if I say input a given cost, what happens is that cost is $2.50 is subtracted from that cost, and then that result is divided by 0.75, and the output will be the number of kilometers one can go for the given cost that was fed into the machine or subbed in. So what we would like would be an equation that represents this inverse function. And in this case, we can see what it is. Take the cost, subtract 250, and take that result and divide it by 0.75. This is the idea of an inverse function. It undoes what the original function did. We know that a function maps elements from a domain onto elements of a range. Like this function does. It maps from 2 to 7, 4 to 15, 6 to 23. The domain here is the set of first elements, as always, and the range is the set of second elements, as always. The inverse function undoes. It maps the elements of the range back onto the elements of the domain. Some call this the pullback. Notice here, 2 was sent to 7, and so in f of x we have 2, 7. Over here in the inverse, 7 will be called back. 7 now maps back to 2. 15 maps back to 4. 23 maps back to 6. And the notation for this function is f. It looks like an exponent on f, but it isn't really. It's just notation. It's the inverse f function of x. We note by examining the inverse that the domain of the inverse is 7, 15, 23, while the range of the inverse is the 2, 4, 6. Comparing, the domain of the original is the range of the inverse, while the range of the original is the domain of the inverse. They've swapped ranges and domains. Assume we have a function which consists of a set of ordered pairs. The inverse function is the same set of ordered pairs. It's just that in each case, x and y have been swapped. If AB is in f of x, then BA is in the inverse f function of x. Examples. Given an equation, determine the equation of the inverse. Solution. To find the equation of an inverse, there's 2 steps. Swap x with y, and then isolate y. In our example, y equals 3x plus 4. Swap x with y. In other words, every y becomes an x, and every x becomes a y. And now isolate the y by dragging the 4 and dividing by 3. And we have the inverse f function of x. It's kind of like when you go to bed at night, you first untie your shoelaces, and then you take off your shoes, and then you take off your socks. For the inverse function, you do the inverse of each operation in the opposite order. So when you get up in the morning, we'll start down here at the bottom and do the inverse. We'll put on our socks, and then the inverse of take off is put on your shoes, and the inverse of untie is tie up your shoelaces. Example 2. Given a function, determine the equation of the inverse function. Solution, execute the two steps. That would be swap x with y and isolate y. There's our original. Y equals 3/2 of x minus 4. Swap, x equals 3/2 of y minus 4. And now it's a question of isolating y. I've done this by multiplying both sides by 2. So this 2 ends up over here with the x. Expanding the brackets. Dragging the 12 over, making it plus 12, and dividing by 3. And then turning it around. And we have the inverse f function of x. Example 3. Determine the equation of the inverse of a slightly more complex fraction. Solution, do the steps, which means swap. So first I've written the original question, and now I do the swap. Y becomes x, and both the x's become y's. And now 2y plus 3 can be multiplied over with the x. So it's x times 2y plus 3. And then expand, use the distributive property and expand over those brackets. And now comes a little operation called sort the terms. We see terms in a row. We want all the ones with y to go on one side of the equality and the ones without a y to go on the other side. So we'll sort the terms. This term had a y, so it's still on the left. This term has a y, so it gets moved to the left. And 3x doesn't have a y, so it gets moved to the right. And we can see that the terms are now sorted. With the terms sorted, we can always common factor and then divide by the factor. And we have our inverse f function. A graphing example. Here's a given function of x. The blue line is a set of ordered pairs such that for every x there's only one y. It's a graph that passes the vertical line test. It's not one of our parent functions, but it is a function. It's a given function. So given this function, which kind of looks like the Big Dipper, sketch the graph of the inverse. Steps. We'll examine the endpoints, or the vertex points. We'll examine this point. It has coordinates -3, -2. If we realize that we're going to do the inverse, we'll have to reverse that. So instead of -3, -2, it becomes -2, -3. And that point ends up down here. Working with this point, whose coordinates are 0, 2, reverse them, make it 2, 0. So this 0, 2, reverse the coordinates, it becomes 2, 0. Join them together and go to the next point. The coordinates are 3, 2, reverse them, 2, 3. So at 2, 3, we'll see the next point. Join it, and the last point is 4, 0. Reverse those coordinates to 0, 4. Put a point there, join them, and label your graph y equals the inverse f function of x, the red line. Note, that's the line y equals x. And the graph of the inverse is the reflection about the line y equals x. The blue line and the red line are each other's reflection across this line y equals x. It's kind of like a mirror. Here's another example. Graph the inverse. Okay, we're given a function y equals 2x squared plus 3, and we want to graph the inverse. The vertex here is 0, 3. Reverse those coordinates, 3, 0. Now pick another point, a point whose coordinates we can tell. I can tell that this is 1, 5, so go reverse them, make it 5, 1. And a point appears here. I can see that this point right there on the original function is minus 1, 5. So reverse those, make it 5, minus 1, and put a point there. With 3 points and a shape in mind, a parabola, we can fill in the rest of the graph. So that's a graph of the inverse. Now we want to find the equation of this inverse. Find the equation of the inverse. There's the original, doing our steps. Y becomes x becomes y. Now you have to isolate y, so we'll take plus 3, drag it across the equal sign, divide both sides by 2, and we have y squared equals x minus 3 over 2. And now, whenever we take the square root of both sides, which is what we need to do to turn this into y, we need to take the square root of both sides of an equation. So in doing that, we always go plus or minus. Here's the reason. Let's take a look in the rough area. If a squared was 25, then a could be 5, because 5 squared is 25, or a might be minus 5, because minus 5 when squared is also 25. So if a squared equals 25, a is plus or minus 5, the square root of 25. Rule: when we take the square root both sides, we put plus or minus on one side. So we'll take the square root of both sides, and we have the equation of our inverse. The top and bottom halves of a parabola that opens to the right. We see that the inverse is in fact a reflection about the line y equals x. Another example, find the equation of the inverse of a quadratic function. Solution. I've rewritten it using standard notation, swap. And now the next step is to isolate the square here. So we'll drag the plus 3 over there. And then we'll divide by minus 5. So it ends up there. And now we'll take the square root of both sides. When we do this, we go plus or minus on one side. I chose this side because this side has 2 terms. It's more awkward. Dragging the minus 7 across, making it plus, and turning it around, we get our inverse f function of x. Review and summary. The inverse pulls back or undoes what a function did. The range of the inverse is the domain of the function. The domain of the inverse is the range of the function, so they trade places. If AB is in a function, BA is in the inverse of that function. For the equation of the inverse, x and y swap places, and then we isolate y. The graph of a function's inverse is its reflection about the line y equals x.